In calculus, we always have some chapter that's covered on exponential functions and logarithms. And we spend the majority of our time looking at how to do calculus things like derivatives or antiderivatives or things like that on these exponential functions, and we get pretty good at the algebra. But when it comes time to do the application problems, usually we don't emphasize quite enough why things are growing exponentially. You know, we see it all over the place in nature and in real life, whether it be, you know, the population growth of a city or compound interest for a bank account growing exponentially. You know, and these types of things, we don't always stress too much why things are growing exponentially. So that's what we're going to look at in this video. Not going to be too heavy on the calculus or whatnot. We're just going to look at the model of why things grow exponentially and what that kind of means. So here we go. So we know this is kind of the generic graph of an exponential growth function. But if we get down to it, why do things grow exponentially? What would make something have this particular graph where it's not only increasing but increasing at an increasing rate? We say that that's concave up. Well, I'll just jump straight to it just to speed things along. The reason things grow exponentially is because the rate of change in whatever the quantity is depends on the size of that quantity. That sounds kind of confusing, but let's put some meat on it. Let's think of an example or two, and we'll see how this actually plays out. We'll start with like money in a bank account. You invest a certain amount of money. We'll just use nice round numbers. Let's say we invest $1,000. And in a year, let's say we get 10% interest. So we've earned $100 interest. So for year two, let me ask you this. If you were to take that $100 interest and just stick it back in the same bank account, so it's not $1,000, but $1,100, would you make more than $100 interest in year two? I think you would. Why? Because there's more money in the account to earn interest. So we see that the rate and change of amount of money in the account depends on how much money is in the account. Totally switch gears. Population growth. I'll bet that there's more people born every day in, let's say, China than in a smaller country like Canada. Now, why? Why are there more babies born every day in China than there are in Canada? The answer is simple. There's more people in China than in Canada. So we see that this connection here between rate and change of a quantity related to the size of that quantity, which is precisely why we have exponential growth. You know, the quantity might grow a little bit, but because there's more, if you take that same percentage growth again, it grows even more, and then do it again, it grows even more until it's off the charts. Okay, so here's how the math breaks down. Here's where the math comes into play. If you were to write that as an equation, here's what we have. We have the rate in change of a quantity over time is proportional to the size of that quantity. And so when we say proportional, we mean within some scalar multiple of whatever that quantity is. So this is what we call a differential equation. Now, most colleges offer a whole class on just differential equations. We're not going to go anywhere near that deep. We're just going to recognize just this basic model here of the rate and change of a quantity being some multiple of that quantity. Now, what would the solution for an equation like this, a differential equation like this, be? Well, you're looking for a function basically whose derivative, right, that's the left-hand side, looks roughly equal to the original. So that's basically what we're looking for. So think through all the functions that you know polynomials, square root functions, exponential functions, logarithms, take your pick. I mean, we know so many different types of functions we've studied, over the last few months. Any of them, have any of their derivatives looked roughly like their original functions? Polynomials, no. If you have a cubic, the derivative of a cubic is not cubic. It would be quadratic because the power goes down. The derivative of a square root function with a radical does not look like the same radical expression. and so on and so forth. But there is one type of function that does look roughly like its original, and the answer was e to the x. If you remember, the derivative of e to the x was e to the x. And so here's going to be the solution. It's going to look a little bit more complicated than just e to the x, but let me write it and then I'll unpack it. So the quantity p of t will be equal to, let me actually leave a little space. I'll come back and fill that in a second. Basically, e, there's your e, not to the x, but we'll have a t, and to account for this extra constant that's happening here, we're going to put k. So I'll have e to the kt. Now, why does this work? Well, let's just look at it. What's the derivative of this guy for the left-hand side? Well, a chain rule says this would be e to the kt times k. And look at the right-hand side. You have e to the kt, if you were to sub that in for the capital P function, times k. So they match. Now, I'm actually going to add in one extra little term here. The general solution would be c e to the kt. So you're allowed to insert just a generic constant here. Why? Well, if you take a derivative of something that has a constant, you'll recall that you can basically just think of it as a tag-along constant. It just hangs around. The derivative of 5x squared, you would differentiate the x squared, but just hang on to the 5. You know, it's that type of idea. So you can insert a general constant here too. So this is exponential growth. So whenever you see some problem that's talking about exponential growth, this is the model that will be the solution to that type of problem. Now, you might have to do some work in regards to finding out what the growth rate is, or finding out what capital C is, or those sorts of things, but that is the general model for any of these problems. So let me be clear on what all these letters are referring to here. It's good to familiarize yourself with this. Capital P on the left-hand side, that's the amount of whatever it is you're talking about after a certain amount of time. Capital P might represent population, or it might represent the amount of money in a bank account, or, I mean, who knows what it could be. I mean, it could be anything that's growing at an exponential rate. C right here, the capital C, that's going to represent your initial amount. How do we know that? What's a good way of remembering that? Well, the word initial kind of hints to me that's when the time is 0, right? Your initial amount. So if t was 0, just do the math. 0 times k is 0. E to the 0 is 1. 1 times c is c. So when t is 0, then the amount would be c. So that's your starting amount. It's your initial amount. Now, out of all these letters, P, T, C, E, K, etc., it could be very confusing which are variables and which are constants. E, never forget, is always a constant. It's always 2.718, so on and so forth. That will never vary or change. All right, the K is the growth rate. That indicates how quickly either the population is growing, or your money is growing, or what have you. If this is a financial problem, and then the K would represent the interest rate of your bank account. So one important thing to remember about that is K is always expressed as a decimal. So if you were doing some sort of financial problem and the interest rate was 4.72%, then we would not use 4.72 for the K. We would express it as 0.0472 by moving the decimal 2 places to the left and expressing it as a decimal, not a percentage, obviously. And lastly, this one's obvious. T represents time. So just keep those things in mind. Now, we need to do an example just to kind of help us solidify this stuff in our mind. Just to keep this video somewhat short, we're going to go and end this one here. This is just a light introduction to what exponential growth means, but we'll go through a typical example in the next video, so I'd encourage you just to go ahead and fast forward to that video.